Beyond the headlines. This is World Insight.
Hello and welcome to World Insight, our special program, the season of AI and basic sciences. I'm Tian Wei. Robotics has advanced at a stunning pace in recent years, and the momentum is palpable right now. The 2026 World Robotic Conference is currently underway in Beijing, showcasing the largest and the latest global breakthroughs. Yet, amidst all this boom, this fundamental question remains. Can we build electronic materials and sensing systems that truly feel like human skin? On this frontier, I spoke with Professor Zhenan Bao, the winner of the ICBS Wu Chien-Shiung Medal in engineering. Bao expects the technology to enable robotics, especially humanoid robots, in the coming years, making them operate more safely around humans and to make better decisions. Professor, these days AI can listen, can talk, can even remember, but cannot feel the sense of touch yet. So what is likely to be the story in the next 1 or 2 years?
Well, sense of touch is a physical signal. So AI stay in the digital world. Mm-hmm. So with the physical information, then it can inform the decision for next steps. I envision in the next few years, touch is going to enter the realm of robotics, humanoid, especially humanoid robotics. Mm-hmm. It's going to happen.
What is the biggest challenge so far yet?
The biggest challenge is there's not enough data. First of all, for
good data.
Right, good data, not enough good data, high quality data to train the model for AI to recognize what object the robot is touching. So that still requires refinement of the hardwares and also get.
So do you see we're likely to have a coexisting in the very near future? You know, not only the humans, but also the wearables playing a crucial part?
Definitely, I think wearables and even implantables are starting to be more and more accepted by the general public because they can indeed help us to inform about our health.
So many would wonder where intelligence begins. Is it only in the brain, or is it also in many of the sensors that human beings have actually supports the brain? Where is the intelligence?
Oh, definitely. Our brain collects information right through our sensory systems. So even our organ communicate with our brain to help with memory. Yeah. There has been studies that if the nerve connecting between brain and the gut is cut, then in the animal they lost memory. So it's very important for the brain to receive sensory signal. Yeah, that's why for humanoid, it needs a lot of sensory information to make them safe around the human and make the right decisions.
Right. At this moment, they're pretty much all programmed. We're looking forward to the time when they can really think and they can really touch.
Well, it will happen.
Final question for you. How do you see the cooperation among basic scientists will be able to speed up the field that you are talking about? And also, how do you, among all the medalists that are sitting here today, how do you see you can contribute even to some of the research that they have been talking about?
I think now the most challenging problems in science and engineering happen at the interface between biology, chemistry, physics, mathematics. Yeah. So it's critical that people in different fields actually collaborate with each other and work together. I see a lot of inspirations and synergy between the work we do and some of the scientists here. For example, Feng Zhang mentioned that kind of understanding the genes and being able to modify the genes could be a way to treat certain disease. And then whether these diseases are going to progress or when do they start to have onset, and whether the gene modification actually changes physiological and chemical communication within the human. That's something that would be for us to develop tools to measure that.
There are a lot of unknowns.
Right.
Thank you so much, Professor.
Yeah,
Congratulations.
Thank you.
Particle physics has quietly rewritten our picture of the cosmos over the past decades, but a ghostly puzzle still refuses to fade. Can we catch the invisible particles that slip through our bodies every second and figure out what they are telling us about how the universe began? So I caught up with Professor Wang Yifang, who received the 2026 ICBS Samuel C.C. Ting Medal in Physics for pinning down a long, elusive switching trick of neutrino at Daya Bay, who now leads the giant underground Juno detector. His work has driven China's rise in neutrino physics, which helps humans answer some of the biggest questions about the universe. Professor Wang, what a pleasure to see you.
Nice to meet you.
Thank you so much for hosting us in your institute.
Thank you for coming.
At this moment, there are trillions of neutrinos going through my body, right?
Yes.
That's how many there are.
There are, I mean, the total number of neutrinos are same as the number of photons in the universe. Every cubic centimeters, there are 300 neutrinos in the whole universe.
Right.
So if neutrino has a little bit of mass, they are going to change dramatically the history of the universe and the future of the universe.
Why neutrinos matter? Well, you are in neutrino physics. Maybe you are the best person I should ask. Why does it matter?
Neutrino is a very peculiar kind of particles. So the whole world are made of only 12 particles, and we call the fermion particles. And among these 12, 3 are neutrinos. So they are very fundamental. Secondly, we know very little about neutrinos. We don't even know its mass. All the other 9 type of particles, we know very well their properties. So, of course, we still have interest, but much less. we are more interested.
Human nature.
Of course, we're more interested in unknowns. Right? So, neutrinos has a lot more unknowns than any other particles in our universe.
If I ask you, would you, Professor Wang, give me a special pair of glasses? It's called neutrino special glass. Of course, it doesn't exist, but what if?
Well, you will see the whole space filled with neutrinos, and every cubic centimeter, there are 300 of them, and stay there, of course, in speed of light, floating around.
I see.
And the fact that we are able to sit here is because neutrino has a tiny mass. If neutrino is massless, the whole universe at the very beginning will be absolutely flat, uniform, without any density fluctuations. If that's the case, there will be no Milky Way, no solar system, and no galaxy, and so on. So we are not going to be sit here. So the fact that we are sitting here very much depends on exact value of neutrino mass.
So the neutrino mass is really the foundation of the universe, so to speak.
It's one of the key parameters we have to know to understand how the universe works. And that's why we try to measure it.
And today it is hosting one of the largest experiments, Juno, for example.
Yes, so now I think we are mature enough, we are able to design and build world-leading experiment. The purpose of the Juno experiment is to measure neutrino mass ordering, which is one of the fundamental questions in the field of neutrino physics. We know that neutrino has a mass, and they can oscillate from one type or another. So we know they have relative masses, but we don't know which one is heavier, which one is lighter. So these are one of the fundamental, let's say, questions we have to answer. And step by step, we should resolve all the neutrino oscillation related problems, measuring all the related parameters, and then we go step further, trying to measure neutrino absolute mass, try to know if neutrino is its antiparticles or not. So the problems are one after another, and we are just one step of it.
That's a good way to say it. The problem is just one after another, isn't it?
Right.
The curiosity is always, there.
Exactly. We still have a long way to go. I think the problems ahead of us is not just something, let's say, can be resolved in 5 years, 10 years, probably 30 years, or even 50 years. So we really had to plan for that.
40 years ago, China has joined the international physics projects, but many wonder why it took so long for China to once again put in much efforts into gigantic physics projects.
40 years ago, we can only go out to join others' experiment to really do the internationally advanced studies. In order to host domestically the world-leading project, you really have to have attractive physics topics. You have to have advanced technologies to be able to build attractive operators, and also you need to have people who are able to do this kind of research. And in addition, you need also to have industrial support that you are able to make these operators and produce raw materials, and being able to provide the needed all kinds of possible support. So now I think we are mature enough. We are able to design and build world-leading experiment based on the existing, let's say, technologies, people, and the scientific ideas. So the idea came out around the year of 2008, and then it took us more than 5 years to develop the idea, and then it took another 10 years to construct the experiment. And now we are actually operate this experiment. So it's a long time thinking, study, prototyping, and finally construct the experiment.
And Juno, by the way, is a gigantic project. It correlates more than a dozen subjects. How do you incorporate all of them into this gigantic project? You yourself participated from day one.
The Juno experiment is very much like any other high-energy physics experiment. So we form a collaboration and we establish so-called bylaws. We have the rules, we have committees, we have a management structure, we have elections. So everything is organized in a way that everybody happy with the
outcome.
As a member of the collaboration, they feel they have the role in this collaboration, and his voice, his opinions being heard. On the other hand, everything is running in a coordinated way, so we can move together to accomplish what we need to.
At this moment, there are quite a number of countries' scientists participating in the same project.
So we have right now 17 countries from all over the world, more than 700 members, and we have more than 70 institutions. So we work together, and we just finished our international collaboration meeting, which is held every 6 months.
And what was the result so far?
Well, every 6 months we have this meeting. We talk about our achievements, problems, and set the goals for the next 6 months, or sometimes for the next 3-4 years. And then we work together, and then we check status after 6 months, see where are the problems, and where there are, say, needed resources to be reallocated, and try to solve, if any, problems.
Where are these scientists come from?
Mostly from China, more than 50%, and then the rest of 40-ish people coming from mostly Europe, France, Germany, Italy, Russia, and other countries. And some from America and also South America.
Wow.
And Asia countries, we also have Pakistan and so on.
That's amazing.
Yes.
To bring all of these together, it's also quite a challenge, but also a fun project, isn't it, for you personally?
Well, we first of all, we have the same goal. We share the common vision about now and also for the future. And we all attracted by the project, by the physics topics. So we all working for the same goal. So I think it's relatively easy actually for us to talk to each other and to resolve any kind of dispute.
And where does the funding come from?
Most of the funding come from the Chinese Academy of Sciences, and the foreign fundings coming from, the respected countries, France, Italy, Russia, Germany. They all have their funding contributions to the hardware of the experiment.
So this is really a crystallization of scientific cooperation?
High-energy physics indeed is one of the model for the international collaboration. I would say one of the best. Indeed, we put all our pocket money, all our government funding, and our time, our people to work on the same project. So it is actually a very good model of the international collaboration.
The Juno project, I understand there's underground 700 meters under the ground experiments going on. Wow, that is really gorgeous.
Well, the neutrino experiment generally required to be in an environment which is very clean. Clean means radioactively. So you have to shield backgrounds from cosmic rays, shield backgrounds from rocks, and so on. So the detector has to be built underground with a large volume of water to shield all possible backgrounds. So that's why we built this detector 700 meters. Why not deeper? Because we are limited by funding. So that's all what we can.
But 700 meters is really already very impressive.
But comparing to other underground experiments, dark matter searches and other neutrino experiments, we are relatively shallow. So
I see.
I think many of them go, say, 1,500 meters or even 2,000 meters.
That's your dream?
Of course.
Next stage?
Well, it's probably not impossible.
How is this Juno project different from the Daya Bay project? Most of the people are aware of the stories related to Daya Bay as well. Tell us more about these two different projects.
On the one hand, Juno is a continuation of Daya Bay from point of people, experience, and also the physics motivation to some extent. But on the other hand, indeed, if you look at the detail, Juno experiment is actually doing something very different. Juno trying to measure neutrino mass ordering, but Daya Bay trying to measure neutrino mixing angle theta 1, 3. So they are pretty different. But we share a lot of things in common, like the technologies.
Artificial intelligence now has become a tool for scientists, AI for science, as we know. How much do you think it can be of support of your latest research?
Well, in our field, AI, more particular, the neural network has been used for more than 30 years. It's not something new. We are very much familiar with. Of course, technology has been improved, and the neural network is different from what we have been used 30 years ago. But fundamentally, it's the same. It's a tool which we are familiar with. It can help us to improve the performance of the detector, performance of the software, and also nowadays with with new AI capabilities, we can even generate our software code. We can generate the figures, the text, and even the tech note using the AI. So it's a very efficient tool, and we have been using it in a very extensive way. Our efficiency has been improved dramatically, but it's not going to change fundamentally our thinking. So still, the physics, science is still driven by human.
How AI can be better used by people in the specific area of research you are working on?
Traditionally, we use AI for pattern recognition, and now we can use AI to generate code, generate text. And in the future, what can be used, we don't know, but we think we may try to use AI with physics knowledge. So we input the non-physics laws so that the AI can do some, say, analysis using existing physics knowledge and generate some outcomes of, data analysis or draw some conclusions from the input.
Where does the imagination, the creativity really comes from in the physics world like yours?
Well, I think there's no rules, no laws, and no formula. It's just sometimes a thinking, discussion. You may end up with 10, 20 different topics, and then you have to choose. Sometimes by accident, sometimes by analysis of comparisons and so on. So it's hard to say, but of course, everyone have their own different taste, and someone prefer this one, somebody prefers another one, but there's no way you can tell beforehand. So sometimes it's...
so for you, it's more imagination or analysis?
I think both. So of course, before we go on a particular direction, you have to have analysis of the possibilities, experience technologies, and the landscape of the world, and see whether it's important enough. I think a very important aspect is that you have to really believe this is important. So there are people choose less important topic, which is slightly easier, and you can get money easier, and you can get your whatever publication easier. But some people take the risk and choose a difficult one. Right. So in the end, it's personal taste, the choice. You could easily fail if you choose a difficult one.
What do you mean? In the public eyes?
In scientific or technological sense, I mean, you choose a difficult one, you may fail because it's too hard to achieve what you designed for, and you have difficulties, and the specification could not be met, and so on.
Do you think difficult ones can attract more peer support, or the other way around, easier ones?
Hard to tell. I mean, there are people prefer difficult tasks. You could convince them easily, but there are people could come say that this is too difficult, you cannot achieve it, and they will veto it. So it's really, you have to take chances sometimes.
Gene editing has leaped from textbooks to hospitals in just a few years, but a humbler question still hangs in the air. Can we fix what's broken in our DNA by borrowing tricks nature already invented? On this, I talked to Professor Zhenan. Tell us more about the latest with the gene editing, because a lot of fascinating things are already happening.
Yeah, I think gene editing is developing very rapidly, and already, for diseases that are inherited and affecting liver or blood, we already have very promising clinical trials underway. Already, sickle cell disease has approved therapy in the U.S. and in the U.K. So I think we're going to see that pace accelerate over the next 5-10 years.
For those who are really interested in the area that you're working on, people see a lot of interactions among gene editing, neuroscience, and also synthetic biology. How do you see these different subjects likely to evolve as a result of the speed of change?
I think biology is inherently interdisciplinary. And so in order to make exciting advances, we need to bring methodologies and knowledge from multiple disciplines together. And so we're seeing that being applied to biology, to neuroscience, and all these other fields. I think moving forward, we're going to see really two exciting directions. Number one, the development of therapeutics for improving human health and treating disease is going to really accelerate, because we're going to have much more information and we can more predictably design new treatment options. The second is using bioengineering to create new biologically based things like biomaterials or solutions for environmental remediation, for energy. And I think that's also going to be very creative and very useful for the world.
Right. From 12-year-old watching Jurassic Park and have more interest in the science to right now being a medalist at the ICBS. What is your advice to the next generation of students and young people?
I think knowledge is cumulative and it accelerates. And I think being a student with so many new tools that allow the research and discovery in science to happen so much more quickly is very exciting. We're going to see biology, we're already seeing biology transitioning from basic research and discovery to more applied. And we're going to see much more of that in the coming decades.
A lot of emphasis on innovation and also basic science. We also see policies coming from different governments, very different. Do you see that there's likely to be more competition, or eventually there's likely to be more cooperation? Anyway,
I think what we need to do is to support basic science, because basic science is the foundation for all of the really exciting applications, useful applications that we're going to be able to do. And so, supporting basic science, build human knowledge base of the world is going to be very important. And I don't think it's competitive. Right? It adds to the collective human knowledge base, and I think that will be what fuels the next generation of innovations.
and that is all the time we have for today. If you'd like to know more, search World Insight. Check out our YouTube channel, follow us on X and Facebook. I'm Tian Wei. Thanks for being with me. Bye for now.
Pod Plus, a selection of the best podcasts in China, covering history, customs, music, literature, and in-depth dialogues. Find your way to a wealth of Chinese culture and thinking, all on Pod Plus.